computer. Okay, one remark at the beginning. If there are any questions, you can ask in English or German as you want. Also, you can do it with the microphone. It's will be much faster, I think, than typing every sentence. Yes, for downloading you don't need anything. You only need to click on the link and then you can download it. There's no password required for downloading. In this POD license key you need only for starting a case in Star CCM+. So then you have to try again. So it's available. It must be on your machine. The link is available. So please try again to download it. Okay, then we can start with first case. So we will create. We will start from scratch. So that means at the early beginning. And maybe you remember the lecture. I think it was today with where the modeling errors are described. There was a very simple case. That means the circular cylinder and flow over the circular cylinder. And today we will start with the inviscid one. So inviscid flow over a circular cylinder. So at first, create a new case. That means click on this plus button or file open new. And then you have to click this tick these two marks, power on demand license, and here under key you have to include this license key I sent by email, and then you can click on OK. And a new star job will be created. So this is the completely clean case. That means up to now there is no conditions, no geometry inside this case. This we have to create in the next step. Okay. So the first step is to create the geometry. You can see on the left-hand side there are a list with the single steps we will do. So we will start with the first one, this geometry. So we can open it. And the next step is to click with the right mouse button on this 3D cut models, and then choose this new one, and the new cut model will be created. So in your case, it also should look like this. So what should I repeat? Do you open the case, or a new case, and then you have to click with the right mouse button on this okay, one second more. So you have to click with the right mouse button on this 3D cut models and then choose the new option. And then you will get this window. Okay, the pop-up window is not seen. Okay, I will close my pop-up and will start again. So, no, I can't delete. So you have to click with the right mouse button on this 3D cut tube models, the one which is highlighted in blue now. Okay? And then there will be an option new. So choose this new and this 3D cut model, one will be created. And this will okay. So I have to start again because something is not working in my case. So I will start in a new case, but exactly the same as before. Okay, so again, geometry, open geometry, then right mouse button on this 3D cut models and choose the new one. Okay, the next step. Now we have to create a sketch in this for this cut modeling. So now click this right mouse button on this feature XY. So the one it's highlighted in blue now. And then choose what's the okay, right mouse button on the XY and then choose create sketch. There's a symbol is a pencil in front of this, and then there's the option create sketch. So click on this create sketch option. And it should look like this. So there are some possibilities to create geometries on the left-hand side. And on the right-hand side, you can see your plane, or your sketch plane, where we will create now the geometry. Zooming inside this scene, you can realize this with the mouse wheel. So use the wheel for zooming inside the scene. Okay, then we choose at first this create point. So this one, which is on the left-hand side. Maybe I check if it is. But you can see my mouse, so then it's fine. Okay, but it's different from the original one. This is crazy. Because the mouse in the video is somewhere else than the mouse on my screen. So click on this button to create a point. And then put it somewhere inside the grid. For example, like here. You will now change the coordinates, so you can put it somewhere you want. Okay? So the next step, now we will change the coordinates, so you have to click again with your mouse button, with your mouse on this node, and it will appear on the left-hand side the coordinates of x and y direction. In my case, it's minus 0.07 in x direction and 0.02 in y direction. Okay, this we will change now by hand. So click on this coordinate, and for x direction, choose minus 0.05, and y direction is 0. Yeah. Okay, so that's our first point. Okay, then we will create the next one in the same manner. So again, click on this first symbol with the points and choose again, set the point somewhere on the grid. And again, click on the point that you will get the coordinates. So the second one will be x direction minus 0.5. And y direction is again 0. Okay. So if I zoom a little bit out, you will see the point is somewhere on the left-hand side. Okay, then another point, the third one. Put it again somewhere and click on the third point. And then we will change again the coordinates. So x coordinate is minus 0.5 and y coordinate is 0.1. Okay, same procedure for the next point. Fourth one. Again, set it somewhere on the grid and then again click on the point and we will change the coordinates. X direction of point number 4 is 0.8. and y direction is 0.1. So the point number 4 will be on the right hand side. Okay, then next one, point number 5. And again, click on the point. And coordinates will be 0.8 in x direction and 0 in y direction. Okay, now the 6th and then the 7th one, so we need overall 7 points. So next one will be here.
Can I ask something?
Yeah.
About 1 point, I typed in 0.8 and it automatically made it 0.79999. Like, is it okay?
Oh, then it's some rounding error, but it's no problem. Maybe if you type the coordinate in y direction, it's also possible to change again the one in x, and it will fit. So, but it's only a rounding error with 79999. It's more or less equal 0.8. So no problem.
Okay.
Okay, then point number 6. So this will be, coordinate will be x direction is 0.05. And y direction is 0. And the last one will be here, so number 7. X direction is 0, and y direction is 0.05. So now we have set all the points we need for the geometry. So we have to connect them. So we'll start with the linear connection. So this means we choose the second symbol. And then we can click, for instance, start on the first node, click on the first node, then on the second, and so on. With the left mouse button, click on the nodes, then you can connect all the points together up to number 6. And 6 you click with the right mouse button so that we stop this. Oh, no. You can also choose the escape button. Yes. So if you click on node number 6, then you have to choose the escape button. In my case, it's one click too much, so I have to do undo. Okay, so if you have clicked on the sixth button, press the escape button. And now we have to create this circular cylinder, or half of the circular cylinder. Therefore, we choose the symbol on the second one in the lower row, the lower line, so that we choose to create this circular or half circular cylinder with 3 points. So click on the left and on the right one below, and then the one above. And afterwards, we created this one. Okay, so now we have created the sketch in the XY plane. That means in the sketch we have now finished. So click on OK on the left bottom button, this one, and we have created the sketch. So next one, we need a 3D body for simulation. So we have to extrude this one. So we mark the sketch number 1, and click with our right mouse button. Then we get a lot of options and choose the extrude option. It's the 8th option from above. And it will look like this one. So there we have to change the extrusion options. The default one is one way, but we will change it to two-way symmetric. And we will change the distance from the default one, 0.1 to 0.01. And that's it. That means after that we will click on OK. And now this volume will be in a gray color. And if we open the first point, this body groups, then a new body is created. And we can close our 3D cutscene. Okay, now we have created, if I rotate it a little bit, then you will see that now it's a 3D body. That means in all 3 directions, X, Y, and Z. Okay. So we can close it with close 3D cut. And the next step is we have to create a part from this 3D cut model. That means we click with the right mouse button on this 3D cut model 1, which we have created just now. And from the options, choose the option number 4, new geometry part. Okay, the pop-up window is again not seen. I will try what happens if I share the whole screen instead of only this one. Maybe then it's better working. So let's check. Okay, now you can see it. Okay, now this pop-up window will appear. And we can choose the default values, okay? So we will take this one and click on OK. And now if you open the part section, then there is created a body, which is the body we created with the 3D cut model. Okay. Next step is to create the physical modeling, and we have to create our simulation, so our grid for simulation. So at first we will create the physics. Therefore, click with the right mouse button on this continua, new, and then physics continuum. And afterwards we have to click on models, again right mouse button and select models. And then we get all the models which are possible to choose. So the next step is to choose the models for our simulation. So what we will do at first, choose, start with 3-dimensional. Then we will simulate a gas. We choose segregated flow. And next step is constant density. Then we choose a steady simulation. And our first step is the inviscid one, so choose the first option of the viscous regime, it's inviscid. And that's all for our first simulation. So again, we choose all the models on the right-hand side, so the inviscid, steady, constant density, gains is automatically chosen, segregated flow, gas, and 3-dimensional. Okay, now we check. We have chosen gas, and we want to simulate airflow. And if you open this gas phase, you will see air is a default one which is chosen from star CCM plus automatically if a gas as a fluid model is chosen. So we don't have to change it now. In our case, we want to simulate airflow, and that's chosen now. Okay. So if you can check the material properties, the density is given, and the density of air 1.18 kilogram per meter power by 3. that's the chosen models, reference values. We use the default ones. We don't change anything here, so we take exactly the default values. And for initial conditions, we need an initial condition for pressure and velocity. So also initialization, we start with pressure, 0 Pascal, and also velocity of 0 meter per second. Okay, it's only for initialization. We start with the whole field is equal 0 for the pressure and also for the velocity. Okay, then we have created our physical models. We've chosen our physical models. So the next step will be create the mesh, to create the mesh. So the first step for creating the mesh, we have to go back to our part region section and our body 1, which we have created. Again, click with the right mouse button and choose the option Assign Parts to Region. Now we have to assign this created part to a region. A region is the one which we will solve in our simulation. Okay, so the region is our computational domain. So the first step is to assign the created part to a region. So click on this Assign Parts to Region. So the body part will be automatically selected. The name of the region will be region, it's fine. And we need only to change one option. So take this second one, the intermediate one, and change it from create a boundary for each part to create a boundary for each part surface. That means we want to set different boundary conditions for different part surfaces. So inflow, one is inflow, one is outflow, one is wall for the cylinder, and so on. So, okay, so change or set this option to create boundary for each part surface. So the first option of the second, That's all. And then we can click on apply. And afterwards on close. Okay. Physics models. So again, I can show also here. So click with the right mouse button on the models and then select models. And then you can choose, well, you have to choose constant density, gas as fluid, inviscid in the viscosity, segregated flow in the solver, and three-dimensional. Okay, now we have created our region. You also can open now this region section, and there you will see there is this region is created. We named it to region, and if we open this region, then there are some sections boundaries. There we can set the boundary conditions and some additional physics condition. But this we will do later. At first, we will create our grid, our computational grid. So, how to create it? I close this lower sections for a better overview. So we have to create it under geometry, and then there is one section operations. Okay, so click on with the right mouse button on this operation, new, and then we will create mesh and automatic mesh. Okay, so new, then choose mesh, and then the first option, automatic mesh. And then again, we get a pop-up window with different mesh models we can choose. So at first we choose the part, it's our body 1. And then we will choose our mesh model. So the first is the surface remesher. That means that the surface grid is remeshed instead of using the cut mesh, because the mesh generated by the cut file is more or less very coarse. So we will remesh it, so surface remesher. If you want, you can choose automatically surface repair. I will choose it now. You can do it as you want. So then you can choose the type of the mesh you will create. You can choose polyhedral mesh, or trimmed means tetrahedral, means hexahedral meshes. And it's also possible to create tetrahedral, but we want to create hexa meshes, so we choose the trimmed cell mesher, the third option. And we also choose the prism layer mesher. And that's it. So we choose surface remesher, automatic surface repair, trimmed cell mesher, and the prism layer mesher. And after we have chosen this grid options, we click on OK. And this new section automatic mesh is created. So there we can also set different options. So let's check the surface remesher. There are different options, but we are using all the default ones, so we don't change anything here. Also automatic repair, we don't change anything. Then trimmed cell mesher, where we tick one part, this perform mesh alignment. So we want to align the mesh on a prescribed position. Okay, so tick this one, and that's it. The other one, all the other ones are the default values. And the next one is a prism layer. And also for the prism layer, we take all the default values. So we don't change anything here. So that's the mesh options. And the next one is the reference or the reference values which we want to choose. So I close these meshes and open the default controls section. So then the first is the base size. Base size means, that's the size we define, and more or less every other size will be defined relatively to this base size. Okay, that means this is a characteristic size. The default one is 1 meter. But as you remember, the coordinates are less than 1 meter, or much less than 1 meter. So we will change our base size to 0.01, okay, to 1 centimeter, 0.01 meter. projection is default used, so it's fine. Target surface size, that means that's the size of the surface cells, and that means that the target size, which is chosen in average. So this is 100% of our base size. That's fine. We use this value. Minimum surface size, that means near curvature or near edges, the surface cells may be reduced or have to be reduced. The default one is 10%, but here we change this value to 12.5%. So this one always means percent relative to base size, and the absolute value is written below. So absolute value of 12.5% of the base size is 1.25 millimeter.
Why are we choosing 12.5%?
Yeah, this is because with our hexahedral, if we want to do refinement, we have to reduce the size of our cells always by a factor of 2. Okay, that means one refinement level means the length will be reduced by a factor of 2. That means we get 2 cells instead of 1.
Okay.
And this, if you continue this, so that means one refinement level is 50%, second one is 25%, and third one will be 12.5%. And therefore we choose here our 12.5%. Because then it will be always, the refinement will always be by a factor of 2. This is very helpful if we use these hexahedral meshes. Okay, so if you do the refinement later in your project, also always use this factor of 2. So that means you have to choose your percentage. If 100% is the base size, then take 50, 25, 12.5, and so on. Or you also can enlarge it, and then you take 100 is the base size, then you take 200 or 400 or 800%. Okay, so always take a factor of 2 for refinement, also for coarsening the mesh.
Okay, so this is related to the base size, you mean?
Exactly. Every value we will add here for the grid is related to the base size.
All right. Thank you.
That means this base size is the characteristical length.
Mm-hmm.
And every other parameter we set in this mesh is related or is relative to this base size.
Okay, thank you.
This is an advantage if you have to change the base size, you don't have to change every parameter. Okay, you will only have to change the base size, and every parameter will be on the same level as before. If you use absolute values, you have to change every parameter of your mesh generation, every length parameter of your mesh generation. Okay? And if you choose this relative size, then you only have to change your base size, and that's it.
Okay. And I'm sorry again, I understood this factor of 2, but why here 12.5 again? I'm sorry.
12.5 means that we will do this refinement more than once. So doing the refinement once will be 50%.
Okay.
The second refinement, so then we get 2 cells instead of 1.
Yeah.
The next refinement will be 25%.
Yeah.
Then we get 4 cells instead of the 1 of the first level of the base size.
Mm-hmm.
And the next step, the next refinement will be 12.5. That means we get 8 cells instead of this 1 of the base size.
So basically we're doing 3 kind of.
Yes. Every refinement is done by a factor of 2.
Okay.
So 100 divided by 2 is the first level. It's 50. Then 50 divided by 2 is the second level. It's 25. 25 divided by 2 is the third level, will be 12.5, which we are choosing here.
Mm-hmm.
The next one will be 6.25. This will be the fourth level, so 12.5 divided by 2, and so on.
Yeah, but I see here it's 3 times. But I didn't understand. You said by a factor of 2.
Yeah, it's 2 power by 3. That means with 3 times refinement. So the refinement, one step, so refinement from refinement, each level will be by a factor of 2, but compared to the base size, it will be a level of 3. So that means 2 power by 3, that means 8 cells instead of 1 cell of the base size.
Okay.
So base size is 1 cell, first refinement is 2 cells, second refinement is 4 cells, and third refinement is 8 cells.
Okay. Now I get it. Thank you very much.
Okay, the next ones will be the default ones. So curvature, default one is 36. That means 36 points over a circle will be discretized. That means for 360 degrees. We use 36 points. That means the distance between 2 points is an angle of 10 degrees. But for our case, it's fine. Surface proximity, also we use a default one. Surface growth rate. We choose also the default one. It's 1.3. How to repair is also default. Number of prism layers. The default one is 2, and this we will change. We will enlarge the number of prism layers from 2 to 5. So set the number of prism layers to a value of 5. Stretching is again, stretching also we will change. The default one is 1.5, and we will change it to 1.3. And the prism layer total thickness, default one is 33, and we will change it to 35%. That we don't use. The next one is the volume growth rate. Volume growth rate means how many cells between each refinement are chosen. So if this is fast, is here the default one, that means that one refinement, the cell will be refined from the, let's say, from the base size to the first level, and the next cell will be refined to the second level. So from 1 to 2 to 4 cells. But this will create some problems in our solution, and also the simulation may be unstable. Therefore, we will change this default growth rate from fast to very slow. That means we create, very slow is, I think, 8 points of the same size before the next refinement level will start. We can check it later on the grid if you have created it. Okay, so we change this default growth rate to very slow. Then the maximum cell size, that means the maximum allowable size of a cell, which we will create. Default one is 10,000%. It's too much. In our case, we choose 100%. So that means the maximum cell size is our base size. Next is to choose a mesh alignment location, and therefore we choose the default one, the 0. It's fine. And that's it. The last one also we don't use. But we have to change, we have now to add some custom controls. So right mouse button, custom controls, new, and then we will change some surface variables. So we have to create this surface control. So then we have to, I've forgotten one step. So before we can continue here, we have to go back to our part section. So we have to go up our body, open the section surfaces, at first then right click on our surface, it's called default. This we have to change now because we want to create more than one surface. Then we also need to, okay. So right mouse button on this default. And then where is it available to? Maybe it's working like this. Split by part curves. And click on OK. It's working. So, but we need a scene for visualization of the surfaces. So go down to the section scenes. It's nearly at the end. Right click, new scene, geometry. So then you will create this geometry scene with our body inside. And now if you go back to our part section with the body, and we have these different parts, you can see if you click on the different surfaces, it will be highlighted in pink in the scene. So we have now to rename these different scenes. So the first one, in my case, is this one. And then must be a second one behind the circular cylinder. This I have to search first. This one. So I choose both together. So click on one, press the control button and click on the second one. And then both parts will be highlighted on the bottom. And right mouse click on one of this and click on combine. That means that both will be combined to one. Okay? So the name is one of the names of the single patches before, but we will rename it now. So this one, so the patch before or in front and behind the circular cylinder on the bottom side, we will now rename to bottom. So you can rename it by typing F2. And then we call it bottom. Okay, the second one in my case is the one on the left-hand side. This will be the inlet, so we also rename this one to inlet. Maybe I can enlarge it a little bit. So this one will be the inlet. The next one is the one in the back. So therefore we rename this patch to back. Then there's the one in the front. So this will be called front. This is the top patch, so it's called top. This one is a cylinder. And the last one is move a little bit to the right-hand side. The last one is the outlet, is this patch. So we rename it to outlet. Okay, now we have changed the names. So first split our surface to the different patches: inlet, outlet, top, bottom, left, right, or front and back, and the cylinder. So that means that we can choose different boundary conditions for different patches. And we have to do again this assign part to region, because we need this different patches for our boundary conditions. So the first step is to delete the created region we had created before, because if you check, boundary is only one surface. Okay, so we can't choose different boundary conditions. So right mouse button on the region and choose delete. This one. Yes, I'm sure. So, and then I have to create the region again. Same step as before. I choose the body, right mouse button, and then assign parts to region. This one. Pop-up window, body is chosen, and I change this second option to create boundary for each part surface. Apply, and then I can close the pop-up window. Okay, if you have done it, we can check now again the regions. The region is created, and if we open the boundaries, then we will see now we have the possibility to create for each boundary patch, we can create an own boundary condition. Okay, but this will be done later after creating the mesh. Okay, if we have split our surface, then we can go back to the mesh generation. So this custom controls, and the surface control. So at first we choose the part surface we want to control. Here listed the patches we have created before. So in the first surface control, we want to change the surface of the cylinder. So choose cylinder.
Sorry, can you repeat it, please? Because I've missed it.
This last step?
The last step, yeah.
So you have created this surface control. So right-click on Custom Controls, News, and then Surface Control. Then you will get this Surface Control button. The first step is to choose a part. Maybe choose the cylinder.
Just cannot find this custom controls.
This is in Operations, Automatic Mesh.
Okay.
I will close the default. And then there are three options: Meshes, Default Controls, and Custom Controls.
Yeah.
So again, Custom Control, right mouse button, New,
Yeah.
Surface. And then in Surface, choose the part surfaces cylinder. And now we will change some parameters. So if we open the controls section.
Okay, thank you.
So we want to change the surface size of the cells. That means the target surface size, and the next one, the minimum surface size. So target surface size, default value is change the parent one. That means the parameters defined in default controls, but this we want to change. So we will switch from parent to custom. And then from values, there will appear the possibility to use a new value. So here we set the target surface size to 12.5%. So again, 12.5 relative to the base size. So again, we choose here this percentage by a factor of 2. So as I told, 100% is base size, next is 50, 25, 12.5, and so on. So we also choose here 12.5. And we also change the minimum surface size. Also, we don't want to use the parent value, so choose custom. And then we can set this minimum surface size. Default one is 10%, but we also choose here 12.5%. Okay, that's the first surface control. But we need a second one. So again, I close the first surface. So again, right mouse button on custom controls, new, and again surface control. Then we create a second one. Now again, choose part surfaces. And now we choose from the part surface, we choose the bottom and we choose the top one. So we choose the patches at the bottom and at the top. What we want to do here is now to disable our prism layer, because it's inviscid flow. We don't want to have prism layers at the slip walls, and therefore prism layer default value is choose the parent values, the parent parameters. So we change this to disable. And that's all. So that with these definitions, we can now create our mesh. So how to create it? There are some possibilities. One is to click on this automated mesh, it's the right mouse button, then you can choose the execute. Or you can also choose the symbols in the upper part here. If you click on the cube once, then also mesh will be generated. Okay, so something happened, and after a few seconds, in this case, the mesh will be created. So, and it's written here in the information part, it's written that the mesh consists of 66,157 cells. So by now we also want to check our mesh. So we will create a mesh scene. So again, go down to the scenes, right mouse button, new scene, and now a mesh scene. And we will see that the mesh is created. Okay, but there is something missing. The boundary layer around the cylinder is missing. To check, maybe in the surface control. Should be. We will create the mesh again. Let's first set our boundary conditions. So, to set boundary conditions, we have to go to the section regions. And region is our created region, the computational domain. And under the section boundaries, we will find the different boundary patches. So let's start with the back patch. That means that is one of the patches which, in our case, this simulation is a 2D simulation. That means we don't need these patches back and front. These are defined as symmetry patches. So we will change. The default one is set to wall, but we will change from the boundary condition from wall to symmetry plane. This one. And the same is done for the front. Also, we change from wall to symmetry plane. Okay? So, the next one, bottom, should be a slip wall, it's fine. Cylinder, again, slip wall, it's fine. Inlet So the one on the left-hand side, this we have to change. It's not a wall. So we switch to velocity inlet. That means we will prescribe the velocity at this patch. And you see, depending on your chosen boundary condition, this symbol in front of the name will also be changed. So this one is a symbol for inlet velocity. This one is a symbol for symmetry. This is the one for wall, and so on. Okay. So for inlet boundary condition, we have to set some values. That means we will open. So flow direction specification will be boundary normal. This we don't have to change. The only one we will change is the velocity magnitude. The default one is 1 meter per second, and we will choose also 1 meter per second. So here we also use this default value, okay? But here you can set, if you want to have a higher speed, then you can set it to 10 meters per second or a lower one or what else, okay? So in this position, you will define your inflow velocity. Okay, top is also fine, it's a slip wall, but we have to change our outlet boundary condition, because this is not a wall, but an outlet patch. So we change it from wall to outlet. And again, we can set some parameters. But in our case, we choose the default ones. So this one and also this one. Okay, so therefore we define now different boundary conditions, an inlet condition, an outlet condition, the symmetry in front and back, because it's more or less a 2D case, and all the other patches are slip walls. So, and now, after we have set these boundary conditions, we have to generate the mesh again, but because this was an error I've done. For each boundary condition which is set, or for each patch which is set as a wall boundary condition, this boundary layer will be created. Okay, we have disabled the boundary layer for the top and also for the bottom one by in the mesh, in the custom options of the mesh generation, but every other patch also was set as wall before. We have changed it now. Therefore, you will see in my scene, for example, there's also, if I zoom in, the boundary layer, it's a front and it's a back patch. Okay, and this is makes no sense. Now we have set this back and also the front one to symmetry patch as boundary condition, and this means that now the boundary layer will not create it at this position. Okay, so it's very easy. I only click on generate the mesh, and it will start to generate a new mesh. And after definition of these boundary conditions, we see the boundary layers are gone at the patches or near the patches which are not defined as walls. So there is only one boundary layer. If I zoom in front of the near to the cylinder, then you will see there's a boundary layer near the cylinder, and that's all. Okay? Okay, now we have created our physical models, we're choosing our physical ones. We have created our grid. And the next step is to create some results for analysis. That means at first we will start to create some derived parts. You see this next part, this derived parts. I will close the one before. So this is the next section we have to use. So we want to create a new part, a new a new section, and we want to create a plane section. Okay, so create on plane. So the region is chosen automatically because there's only one region. But now we have to we have to define our section. Where should it be? Where should it be? So the first plane section should be on origin is the origin. That means all components are 0. So x is 0, y is 0, and z is also 0. And the normal vector should be in z direction. So we will change it to 0, 0, 1. Okay, that's the first. And I don't need a displayer here, so I tick this no displayer. And then create, but click this button only once, because if you click it more than once, you will get more than one of these plane sections, okay? And it's always the same. So we want to have two other plane sections. Therefore, we have to create to modify our origin and normal values. So next one is the plane section at the bottom. Therefore, we select at first the input parts we have to modify. Instead of the whole region, we only want to have some parts of the region. That means we want to have bottom region patch and also the cylinder patch. And the region we have to disable. We have to disable at first all, and then we have to choose bottom and cylinder. Okay, only these two patches we want to have. Okay, and the origin and normal, it's the same as before. So again, 0, 0, 0, and normal direction is in Z direction. That means 0, 0, 1. And click again once, create. So, and the third plane section will be similar, but now we will choose the patch at the top instead of the bottom ones. So again, select regions, then remove bottom and cylinder and take the top one. And again, okay. And origin and normal, the same as before. So click again once, create. So then we have created 3 plane sections, and we can close this window. So click on close. And if we now check or open our derived parts, then we will see that there are 3 plane sections. Plane section 1 is the one in the middle of the whole region. So on this plane section, we will, for example, visualize the pressure or velocity or something like that of the flow. When then the plane section 2, it's the one below. So you see here it's a line. It's this pink line at the bottom and on the cylinder. This will be control points for our forces. Therefore, I will rename this plane section to plane section bottom. And number 3 is the one on the top. See again, here's this pink line at the top patch. And therefore, I will rename this plane section to plane section top. Okay, that's all of the derived parts. Next one is solvers, but solvers we take the default values. For instance, for steady, there is no option partitioning. Also, we choose the default one, and then we use this segregated flow, and we will change the parameter, the under-relaxation factor of the velocity. Default one is 0.7, and we change it to 0.8. And the same for the pressure. Default one is 0.3. And therefore we will change it to 0.2. Okay, stopping criteria we don't change. The first one is the simulation should stop after 1,000 iterations. This we choose. And the stop file we don't use. So the default one is used and we don't have to change it. If you want to run the simulation for a longer time, you can enlarge this value from 1,000 iterations maybe to 10,000 or what else. You can choose what you want, the number of iterations. But in our case, the 1,000 will be okay. Okay, and then we need some functions for the forces. This will be created in the report region. So again, right mouse button, new report, and then under the first option, flow energy, there is a possibility of force. So we choose this one, a force report. So it's created, it's called force 1. In my case, I will rename it to drag force, drag. So unit Newton is fine, laboratory is also fine, direction is, it should be drag, so in x direction, it's fine, 100 means x direction. Pressure and shear, in this case it's fine, we don't have shear in this case because it's inviscid, but in the next exercise it will change to laminar and therefore it will be shear included. So in our case we use also here pressure and shear. But the only one we have to choose is the part. That means we have to choose the patch on which the drag is created, and this will be for our cylinder. We want to calculate the drag on the cylinder. That means we choose the region, and the patch is cylinder. That means this report will calculate the drag force acting on the cylinder. Okay, and okay. And then for comparison, there's a second report. We want to compare the pressure at the inlet and the outlet. So, therefore, new report. And it's user, and where is it? Surface integral. That means we want to integrate the pressure over the whole surface. So new report, user surface integral. Then we create a surface integral 1. This I will rename to pressure in. Pressure in. So now we have to select our function. As I called it pressure, here we want to choose the pressure, so click on function, and then PV pressure, P is pressure. Okay, and we have to define our parts where it is calculated, and this should be the pressure integration at the inlet, so regions, and choose inlet. And that's all. And then we do the same for the pressure outlet. So again, reports, new, user defined, and surface integral. Now I rename it to pressure outlet. Again, function is again the pressure. And parts, now we choose the patch outlet of our region. Okay, now there are only a few modifications we have to done. So the next one is to create the plots. This means the XY plots. The default one is the residual, which are plotted for each simulation, but we also want to create an XY plot for the pressure and for the velocity. So therefore, at first, we create an XY plot, so that means right mouse button on plots, new plot, and then this XY. So we create this one, I call it XY plot pressure. So what we have to include the parts where it should be calculated. So in this part we choose our derived parts. That means our plane section at the bottom and the one at the top. Okay, so as parts of this plot we choose the derived parts, plane section bottom and plane section top. The one we created in the section derived parts. Okay, I think that's all. So we will do the same for the velocity. So again, plot, new plot, XY plot. This will be XY plot for velocity. And parts, we choose again or derived parts, bottom and top. Okay, so scenes we can create also after simulation. So maybe we will start our simulation. So how to start it? At first, you have to initialize your fields. This will be done by clicking on this green flag. If you click this once, then it's written initialize solution is finished. And after it, you can start. There are two possibilities. There is one slowly running man. Will do only one step in your simulation. And there is this fast running man. This will be run the simulation up to your stopping criteria. So if you click this fast one, you will see residuals will be plotted. And after some time, I will zoom in a little bit. We will see our results. You will just see residuals will go down. That means solution is converging. So after simulation is running, we can, during the simulation is running, we can create our scenes. The next step, we will create, let's say, one scalar scene of pressure and one of the velocity. That means we will create scene, right mouse button, new scene, and then choosing this scalar. Then we will open the scalar one, open the scalar scene, then open the scalar. And we have to choose here the parts. So if we click below on parts, we choose now our derived parts, the plane section we have created in the center of our region. And OK. And now we have defined our plane section, but we also have to choose a scalar field. In this part, the first part should be the pressure. So we choose again, selection, and then choose pressure. Okay, and you will see the pressure distribution at our plane section. So you see these black lines, which are due to the outline. So I don't want to have this outline, therefore I will deselect parts in the outline. And then I only get the pressure distribution, and you also can see that there is it looks like a step function. I want to have a smooth distribution, and therefore this can be done if I check the scalar option and then change this automatic to smooth filled. Okay, and then I create this smooth pressure distribution. It's only an interpolation due to the cells.
Could you please repeat how do I get this scalars? I created a scalar scene, and then
so then you have to include your plane section in the parts. So open the scalar.
Yeah.
And then click on parts.
Yes.
And then below, you have to choose your derived parts and then plane section.
Okay.
And and then it should appear.
Yes.
But you also have to select your scalar field. There I choose the pressure.
I choose selecting that. Thank you.
Okay, there's one possibility to easily check the mesh in the scene. So again, it's the upper part. You see this, this cube. If I click once on the cube, I can check how the mesh is created, or how the cells are distributed in this plane section. And if I click again on the cube, the mesh is gone. Okay, so this is very fast switch between visualization mesh or not. Okay, after this scalar scene of the pressure, we want to check our velocity. So therefore, we add an additional scene. So again, right mouse button on scenes, new scenes, and now a vector scene. Then we have to check again vector, and we need to add a part. Again, we choose this plane section of the derived parts. And vector field, the default one is chosen is the velocity, so that's fine. But I want to didn't want to see vectors, but I want to see this line integral part. This can be chosen by vector. And then there are different options. There is one display mode. If you want to see your velocity vectors, then choose this glyph. It looks like here. So you see some vectors for different cells. But I want to switch this one to the line integral convolution. And then it's, first have again to deselect the parts in the outlet, because these black lines I don't want to see. So I deselect the parts in the outline. And here now it's you can see how the velocity is distributed. So the magnitude of the velocity is visualized by the color. So red means high velocity, blue means low velocity. And the position or the direction of the velocity is visualized by this lines, which you can see in the plane. Again, if you prefer vectors, then you have to switch the line convolution again to glyphs. But then you have to define maybe the length of the vector. This can be done under glyph. There are different positions you can define the relative length. Maybe 5 is too large, maybe we choose 1. You see the vectors will be much smaller. So you can play with these parameters. Also, the distribution of the vector, maybe we don't want to have geometric, that means defined by our cell size. Maybe we want to have a uniform on the screen, so we can change it here. So you can play with your own case how to visualize vectors or the magnitude of the velocity as you want. Okay, I will switch again to this line convolution, because it's much easier to see. Okay, so one important step I forgot always by creating this case. From time to time, you have to save your simulation. So you need only to click on this save button, the third one in the upper, and it will ask, okay, how to name it. Now you can rename it to a name, to another name. Default one is star, and the next where star one or something like that. So you can choose your name as you want and save it on your disk. So this is also preferred for the next exercise, because we will continue on this case. We will choose, or we will modify the boundary conditions and also the physics models to create a laminar case and check what happens. So we can check our plots as last step today. So residuals we have seen. The result is, in my case, it looks like this. So you see, residuals are still increasing, decreasing. So, but it's decreasing all the time. So the simulation is converging. That's fine. So maybe we need some time iteration steps more to receive the accuracy of our machine. But it's still converging. So let's check the other plots. So if you click right mouse button and open, it will open the plots. Okay, no, nothing is seen. I have to check what happened. Everything is correct. Let's check this one. I have to check the scalar function. I thought. So again, here I have to check our pressure. So this should visualize the pressure distribution. So I choose pressure as a scalar function. And then I will receive the distribution of the pressure at the bottom wall, which will be the red one. The red distribution due to the red circles. And at the top wall, there's the one with the blue, is visualized by these green circles. And for the second one, the one of the velocities, there again I have to change this value scalar function. There I want to have velocity in x direction, therefore I choose velocity and the component in x direction. So this one. I is the velocity component in x direction, j the one in y direction, and k the one in z direction. Okay? So I choose this one and also open the scene. And now I see velocity distribution. The red one again on the top wall and the green one on the bottom wall. ideally, the distribution should be symmetric. The velocity distribution as well as the pressure distribution, both should be symmetric. But if you zoom in a little bit, for example, here in the velocity distribution, you will see velocity at the front stagnation point and at the rear stagnation point is a little bit different. This is due to errors in our simulation. For instance, in this case, it's due to discretization and iteration errors. So there are small errors because every simulation is an approximation. And it's very important to estimate these errors in our simulation, okay? So the ideal solution will be the symmetric solution, but with our simulations, we don't receive this exact symmetric solution. It's a little bit unsymmetric. Okay, and this is due to our errors we have done in our simulations. We do more or less in every simulation we do errors, but we have to guarantee that these errors are small. That means that the solution we receive are good enough for our analysis. So, but I think the more theoretical details about this will be done by Professor Pelch in the lecture. And that was the first exercise. This is inviscid case. As I told again, the next lecture exercise, we will switch to a laminar case, so we will modify this case. So please save this simulation case. We will continue with it in the next exercise, and the next exercise will be in 2 weeks. So it will be on Friday. Which date is it? Friday on the 27th of November. Okay? So then I will close the exercise for today. And the next exercise, as I told, in 2 weeks. So then we will continue with our created case. Okay, are there any questions at the end?
Yeah, we just saved it using the save option. That would save the case and the result.
Exactly. Then it's asking for a name. You can choose the name you want and where you want to save it on your disk. And the next one you can load it in the simulation.
Okay.
So that you don't have to do it all again.
All right. Thank you.
Okay, then I will close the exercise and see you again in 2 weeks for the second exercise. Thank you for participating. Goodbye.
نهاية هذه الجلسة. موافق.